our HHVM team, and is going to give you the rundown on some of the, quite frankly, incredible performance improvements that we've made there. And so all the way from Boston, I'd like to welcome Ed. Take it away, please.
Thanks. I'm really excited to be able to tell you about some of the stuff we're working on today. First, I'll just start out. I had a couple slides at the beginning originally, motivating why performance matters, but I cut it because I think we can just take it as self-evident that performance is important. We're really passionate about performance, and taking a dynamic language that is not, always the most well-respected language for being fast, and peering inside of it and extracting the fast program that's living inside this dynamic program without any of the information that you need to know being there in the source code, there's an art to that, and it's a fascinating art. I've been interested in this for a long time, and so I'm excited to be able to tell you about it. Also, the context is that we run our software in big data centers, and efficiency is super important. We bend over backwards, we do somersaults, we tweak little 1% every time. We even stand on our heads to become one with the machine and understand what this thing is doing. So what I'm going to do is just walk you through how our team works, what is kind of the workflow for how we do optimizations and how we think about it, and then describe what the workload is. What is a PHP really doing when it's running on a CPU? And so I'll tell you what we do, how we do it, and I'm going to get into two examples of how we optimized arrays and then how we optimized code, and then just wrap up with what other things that we've been working on. And I'm going to not go into much detail. So I'm going to give you some detail about what we're doing. None of it you have to remember, and I'm hoping you'll find it fun. My kids watched this interesting show called The Magic School Bus, and what I want to relate to you is that just like in that data center picture that we recently went down and got to go visit this data center in Forest City. It was really fun. And it's this giant building full of computers. And the amount of space in the building is enormous compared to the amount of space taken up by the computers. And all of that infrastructure is designed to just funnel cool air in and hot air out and electricity in and data in and data out. And I felt like we were stepping down into the computer because it felt like the data center was a computer, and I got to go inside the computer and actually see what's actually happening inside. And so we're going to get in our Magic School Bus, and I'm going to take you down inside a CPU, and we'll see what's happening inside the CPU and what it feels like for that CPU to be running PHP. So what do we do? Well, here's a question for you. Let's say you have an elephant and you have a refrigerator. Pop quiz. How do you put an elephant in a refrigerator? You open the door, you put the elephant in, and you close the door. So there's no magic. There's no guys in white coats. We build things. We measure how fast they run. We come up with some ideas for hey, this looks slow. We could tweak this. This thing looks slow. We could tweak that. Some of the ideas are bad, and we want to fail. We want to stop working on the bad ideas as soon as we can. And some ideas are good, and we want to bang them out as soon as we can. And sometimes they take a long time, and some of them are short time. So our team has an interesting rhythm that's sort of punctuated by lockdowns. And I'll tell you the story about lockdown. Many years ago, 5 being many in this industry, we switched over to HPHP. And then we began working on HHVM. And we needed to make HHVM faster than HPHP before we could deploy it. And we had a end of 2012 goal of doing that. And early in 2012, actually right around now in 2012, we still had to triple our speed in HHVM before we were going to be able to replace it. We were only running 30% of the speed. We got to about 2/3 of the way through the year, and at the rate we were going, we still weren't going to close the gap. And so we needed to change behavior. So we all packed up our computers and moved to a sort of a neglected section of the campus here where there was nobody bothering us, and we changed our workflow to basically just rip through as many ideas as quickly as we possible and rack up 1% wins as quickly as possible. And we gave ourselves 6 weeks, and then we'll just take the holidays, however fast we get. Whether we make the goal or not, we're just going to work really hard and then take a holiday. And much to our surprise, halfway through the 6 weeks, we hit our goal, and then we kept on going for 3 more weeks, and we had a blast. Our team came together, we gelled, and it was really exhilarating to crank up that performance. And if you've ever seen the charts where we talked about this publicly, you see this slow growing curve and then an inflection point, and we got much faster very quick. that was fun. And so since then, we've decided to do it again and again and again. So that first one was November of 2012, and Thanksgiving holiday was our break. We did it again in May in 2013, and we got a nice big win, and that worked well. And then we did it again in the fall of 2013, and we blogged about that. And that was when we also expanded the lockdown idea and included the open source parity hacking, which you guys hopefully saw the post on that. And then after lockdown, you take a rest, you take a break, you clean up all the technical debt that you incurred while you were locking down, and then you repeat the process. So this is a picture of what it looks like in the middle of a lockdown. You know, you're more than halfway through, you're not there yet, and you're working really hard, and you hope you get there. The moral of the story, this was the November last year. We did make it, and I'll tell you how we made it. You'll see that step function in there, and that's an interesting story all by itself. Anybody know what the step function is? All right. So, how do you take 1,000 elephants and put them in a refrigerator? Well, it's simple. You build a really big refrigerator, you open the door, you put in 1,000 elephants, you close the door. Simple. This is what we do. So what we're doing is we need to understand how PHP inflicts pain on the CPU. What does it do that makes it run slow? And to really sum up the whole problem, it's all about memory access. Like, if we get on our magic school bus, we'll see how the memory access looks. So we understand that, we optimize memory access. We add muscle to the compiler to enable it to remove more memory accesses. Again, I'm oversimplifying the problem, but that's where you get the cycles from, is removing the memory access. And then repeat the process. And some of those iterations take a long time. If you have to build an entirely new algorithm, that's not a good idea during lockdown. And sometimes it's a matter of like removing something clowny or tweaking some code path or adding an inline directive to a C++ function, and then, you know, boom, you get a 1% win. If you've got 20 people and you get a 1% win per person per week, 3 weeks, you get 61% wins. And in this world of math, they don't come out to 60% faster. They squash down and interact in funny ways, but you do get good wins. So you have a CPU. You know roughly what it looks like. What does it look like when it's on PHP? And of course, what does it look like when it's on Hack? PHP is essentially a dynamic untyped language. So every step of the way, you're discovering what the program is trying to do. And Hack is a gradually typed language, so it's got some advantages, but still there's a lot of discovery going on. So our PHP workload, now I'm talking about what we're doing at Facebook. And hopefully other apps are similar workloads if they scale them up, but not always the same. But I'll just describe what ours is like. We use a lot of APC. APC originally stands for Alternative PHP Cache, which is a bytecode cache. That's not at all what we use it for. It's just an in-memory key value store. We boot up the server with a bunch of configuration data, translation data, a lot of like interesting stuff, and then it reaches sort of a stable working set with live data as well. We have a huge code base. You've heard this mentioned many, many times. It's giant. And what that means is that the code that's actually running is huge. It's a small fraction of the actual size of the source code, but it's still a big working set. We have very large request heaps. If you go to facebook.com and hit a news feed, that request burns a lot of power to generate the results that we're after. You got a lot of different pieces of information being fetched from different sources and processed and then delivered. And that takes upwards of 10 to 100 megabytes, depending on lots of factors. And that 10 to 100 megabytes is arrays and strings. And it just makes me cry as a compiler engineer. Arrays and strings, arrays and strings. And we've added objects. People use objects. They're very useful. So are collections. And you can go back and run a memory profile, and it's arrays and strings. So we put a lot of energy into arrays and strings. And I'll give you an example of what we've done with arrays. There's a lot of overlapped I/O. Everything in PHP comes from some external source except APC. You have to get it out of some external source, do something with it, and then your request goes away and all your memory is erased. So there's a lot of data moving into the CPU and moving out. And of course, because there's overlapped I/O, you need a lot of threads to keep the CPU busy. So we have hundreds of threads. So let's visualize this workload. Are you still with me? This is what we're going to run. We're going to try to run this on a CPU. So here's our HHVM process. There's our initialized cache of data. There's some code. And when we're in a steady state, this is kind of the situation before a request comes in, even after we've initialized. So you might have a few hundred megs of code, you might have a few hundred megs of APC, but that's kind of the situation, ignoring simultaneous threads for now. There's like no other threads running. And the person comes along, and they make a request. So I have a request heap that initially just contains, like, what are they after? Get some page, here's some headers, boom, that's really tiny. You go off to Memcache or MySQL, you fetch a lot of information that the user is asking for, your request heap gets bigger. And then you hit some more and some more and some more and some more because you've got this really fancy page with lots of information, lots of data sources. That request heap grows. It may grow because it's been optimized already, people are stashing data. It may grow because there's a cycle and we've failed to remove the cycle. That's something we'd like to work on. But to sum it up, it grows. And so what's happened is we've pulled all this data into the memory of the computer. We've done a lot of processing on it for, let's say, a second. And then we're going to toss it all away. So we're just like in the data center. We're bringing all this stuff in. The actual work is this piece, and then all this stuff comes out. And so we have to have some empathy or some sympathy for what we're doing to this CPU. So get on the bus with me. We're going to shrink things down. So we're going into our data center. We're walking past the door. We're feeling the cool air coming in. We're going upstairs. We're looking at all the wires and the network and the heat, and it's all around us. We can go downstairs and feel the hot air blowing off the back of the computer on us. So let's do that with the CPU. So that's what a CPU looks like if you look at it really close. It's like the size of your thumbnail. And this is a big, beefy CPU. This is an 8-core Sandy Bridge CPU. Most of that die area is not CPU. You've got like some cores on the left and some cores on the right. It's like less than half of the die area. Big, huge cache, big, huge I/O, big, huge memory controller. And then inside those cores, you've got like lots more cache. So the actual core part that's doing computation is like probably less than 10% of the die, 10% of the power. It's just down in there waiting for data to get to it. And it's running at an insanely high clock speed, like say 3 gigahertz. And so all of that wiring and all of that is just to get the data down into the CPU. And that core is not just like a tiny little core. That core is a freaking supercomputer, right? It's actually like 8 functional units. It can do double at an insane, double precision math at an insane pace, integer math at a insane pace, multiple branch units. It's designed to like find all the parallelism in your code and run it all at the same time. And so all we have to do is get instructions into it and data into it so it can do its job. So magic school bus time. To really get a sense for what's going on inside the CPU, let's walk down. Let's shrink time a little bit. So first of all, we're living in the world of seconds. Like you can think in the term of seconds. A millisecond is already 1,000 times faster than that. That's the world of networks, right? You send a ping, it takes milliseconds to go somewhere, milliseconds to come back. If you could somehow ping through a fiber optic cable that way, around the Earth, and then come back this way, that's 130 milliseconds or so. And coast-to-coast pings are typically 60 milliseconds and so on. That's the time scale of milliseconds. So we just shrank from real-world size 1,000 times smaller. We're like sitting in network wires, running around in wires. We can think about packets as they go by, like there's a packet, there's a packet, there's a packet. That's what a network router sees at the millisecond scale. Now we're going to go down to microseconds. That's 1,000 times smaller. So at this scale, it's 1 million microseconds in a second. So we're not talking about networks anymore. We're talking about, speed of light 750 feet. Like I go out, take a lap around the building, come back in, that's 750 feet. This is like the scale of SSD or really, really slow RAM. Like ask for a byte of memory, ask for a block, get a block back. A block of data just went by, a block of data just went by, maybe I did some bus transactions, that's what's going on. Network packets. Like if a network packet comes by, it's like, okay, send it off. Let's wait 1,000 ticks, right? We're at the scale now where milliseconds take 1,000. That's like, do the math, it's like minutes. It's like a third of an hour. We're going to wait 15 minutes. I just sent a network packet. Call me in 15 minutes. We'll wait for that network packet to come back. This is why you want I/O close to a CPU, right? Your disk needs to be close. Your SSD needs to be close. Now let's shrink it some more. Nanoseconds. There's 1 billion nanoseconds in a second. If I just send a request to my SSD, now I have to wait 15 minutes to come back and get this data back off the disk. 15 minutes. I can process in at the nanosecond scale, this is inside the CPU. You're running at 3 gigahertz. That means you have 3 clock ticks per nanosecond. And you have all these functional units that can execute an instruction every clock tick. So in one clock tick, which is 3 of those in a nanosecond, so let's say 3 clock ticks, I can now process 8, 20, 30 instructions, 20 or 30 instructions, 20 or 30 instructions, 20 or 30 instructions. Oh, I got to talk to the SSD, 15 minutes, right? So if your system's swapping, like, okay, 15 minutes, like let's play some Pokemon, let's play some video games. We're just going to sit and wait. We have nothing to do until the system swaps the memory in for me to work. And the CPU is going at 3 gigahertz, right? Not 1 nanosecond per clock tick, but 1/3 of a nanosecond per clock tick. So this is the time scale of the CPU. We're down in the CPU, 30 instructions, 30 instructions, 30 instructions. And by the way, that's if you use all the functional units, and most code doesn't do that. So it's really like one instruction, and all this silicon is sitting there wasted, waiting for an instruction. So we have all this silicon. The CPU is, hungry for work. Please give me work. And we got to give it some work. We want to stay CPU bound. These things are way more expensive than RAM. So if you're all RAM bound and you're not using your processor, you're sort of out of balance. So we've got dozens of these cores we've thrown in there. I'm only going to show 2, but you have an idea of what it looks like if you have lots more. And our goal is to keep the cores busy. So this is the first way we're going to try to keep busy, is we need to bring some memory into the cores, right next to the core, and give it some work, right? I need to run some instructions. They need to be right there. I need to do some computation. The data needs to be right there. And so I've got an instruction cache and a data cache. These are small. These are like 32K. Smaller than an old 640K PC, right? The tiny, tiny, tiny amount of memory, but it's enough for like a loop in a piece of code to not get stalled. A loop can run in that space. And if you have a really, really tiny language, then a whole interpreter could run in that space. But that's what we've got. And the delay is 1 nanosecond, right? So even if I have to go to my first cache, 30 instructions just went by. That's a nanosecond. 1 nanosecond, 1 nanosecond. So you really have to keep those things busy. And that's not enough, because with 1 nanosecond going out to 100 nanoseconds, you need more cache. So next generation chip, we have more cache. It's now 4 nanoseconds to go by. So if I can't get something out of my initial 32K cache, right, I'm going to wait 4 nanoseconds. Like, nothing to do, nothing to do, nothing to do, nothing to do. Ah, now I can do some work. That's still not enough. So now we have another layer of cache that's shared between cores. On a typical server processor, this is like 20 megabytes. And the access time is 12 nanoseconds, right? It would be excruciating to listen to me count off 12 nanoseconds. So it's already a problem if you keep going to L3. And what's really happening is there's never enough cache, right? We're talking about lots of data, lots of code. We're constantly going past that. And the bottleneck is down there. So if you can imagine a data structure with a pointer in it, and as soon as you follow that pointer, you're off in la-la land. You're just waiting on RAM. 100 nanoseconds. That's like a minute and a half. So I can just sit here and wait a minute and a half. Well, every second I could have run 30 instructions. I'm just waiting a minute and a half. So that's what's going on. So let's pop up a little bit. Let's think about the data structures that we're using to represent PHP arrays. They're a well-loved data structure. Somebody said something about duck typing earlier, and I thought about arrays, and I'm like, wait a minute. Looks like a duck, acts like a duck, must be a duck, right? No, they're like a platypus. It may look like a duck, but it's not a duck. Sorry about that. So, arrays. So this is a Zend array. I don't know if this is an app's name, but this was a data structure in hip-hop in the early days. And it represents an array with a header pointing to somewhere else in memory a bucket of hash entries, which are just more pointers. And then each value you put in the array, like say you have an array of Alice with a user ID, Bob with a user ID, and Carol with a user ID. Each thing, the basic array, the hash table, and each value is pointed to in a separate piece of memory. Each time I chase one of those purple arrows, one of those pointers, we're hitting DRAM on average because the working set's so big. So a minute goes by, chase down a pointer. Well, okay, now we can go look at the next pointer. We'll wait, and the CPU is just idle. And we found this by looking at perf and looking at our Linux tools and finding out a way to optimize. So our next generation array data structure was what hip-hop VM first had. We called it HPHP array. And the idea with this data structure was to put the values closer together in memory so that you can access them faster. So if you go to the array and then go to the data and you're iterating through an array, which is a common operation, now that data is all the way, the first time you touch Alice, all that data gets pulled into that tiny little L1 cache, and then Bob and Carol are going to be right there, right there. You're not going to wait. Presumably you're doing something with this data, so by the time you do something and come back to get the next thing, you certainly can overlap that tiny little 1 nanosecond delay that you have to get to L1. So this was a big win for array speed. And then the most recent incarnation of HPHP array was renamed to mixed array. You've seen the mixed type, and that's what it's for. It's an array that can hold mixed types of keys, integers and strings. And you see the missing arrows. We've put the whole thing together in memory, so if you access the array, it's going to likely get pulled into cache, and you can get to it even faster. But arrays are like platypuses. They're not always maps. This is actually an array that's looking like a map. Lots of arrays are actually vectors. So we have a packed array, which has exactly the layout that you'd expect for a vector. One chunk of memory, all the values laid out. And most languages that have real arrays have them like this, and our runtime does this as well. We can automatically convert a packed array into a mixed array if necessary. Like if you have a bunch of values, keys are 0, 1, 2, and you throw some garbage in there, we can escalate it very quickly. So the second example I want to show you is how the compiler works. So the thesis of what I just said was arrays with lots of little blocks of memory are slow, and arrays with one block of memory are fast. That's the data side of the CPU, right? Now let's talk about the code side of the CPU. So you've got a piece of code. Logically, in this piece of code, there's really three things happening. There's a check, there's an error path, and then there's a normal path. 3 logical blocks of code. So with HHVM's Tracelet Compiler, which is what it first launched with, we will discover what's going on one block of code at a time. So as the code runs, we'll discover that C is, for example, is an integer, and we'll compile that first chunk of code, and then synchronize everything out to memory and go back to the runtime to see what happens next. And let's say what happens next is the common case of just returning C because it's not negative. Well, then we'll compile that next piece of code. We'll guard again that we're making sure it's an integer, and we'll return C. And hopefully these things will be close in memory, but not always. It just depends on the behavior of the program and which threads are compiling at the same time. And sometime later, the other path will be taken, and we'll compile the other path and stitch everything together. So at this point, the program's stable. It can keep running like this. But there's redundancy in there. Each of these arrows represents saving a bunch of values out to memory and loading them back in and then checking the types again. And we haven't done anything sort of intelligent with how these blocks connect together. So that's where the region compiler comes in. This is a project we're working on now. It's not fast enough to go into full-blown production, but we're getting there. And just like we saw with arrays, the idea here is to put things close together in memory and eliminate the unnecessary loading and storing of data values. So in this case, we've watched the program run for a little while, and we've seen that it usually takes the common path, which is not to print an error. And we compile that all as one unit in memory. There's only one guard, and there's no loading and storing in between those two blocks. And so we've saved a bunch of memory traffic. And that's good. We want to save memory traffic. Every one of those memory traffics is, is a coffee break for the CPU. So we want to save those. And then occasionally, sometime later, you may go the other way, you print an error. That'll be another contiguous block. And if that branch happens to be unpredictable, where you go both ways a lot, those two will be good compile blocks. We don't make the CPU go one way and then come back to where it was before. We go the other way and we don't come back, and that also is better for cache behavior. So this is how you make the CPU fast, is you just keep giving it data. That's all you got to do. If you can give it more data, it will be faster. All the rest of the computer science is basically just funneling data in and out of the CPU. So we're done. We've held that little thing in our hands. We put it back into its rack, plug it in, turn it on, get data in and out. We're going to leave the data center and enjoy and reinflate to our natural human size. So now nanoseconds are going by like blazing like the speed of light, and we're back in human timescale, where we can talk about what we did last year and this year. I don't even want to think about what a year feels like to a CPU. So last year, we doubled the speed of the VM. That was really invigorating and fun. We put in a new JIT compiler. The region compiler I mentioned takes advantage of the new JIT compiler that we built last year. The one we originally shipped when we first turned HHVM on in production was replaced with a new one that is just better at optimizing, even though we didn't change the shape of the code. We made strings flatter. I showed you how we made arrays flatter, but we've done the same thing with strings. So if you look at a string in memory, it'll be like a little bit of header with some size and a hash code, and then just bytes. And they're all together. There's no intermediate pointers. We did packed arrays, as I mentioned earlier. And then we did one more thing, which I alluded to earlier, the step function in our performance graph. One of the things we've struggled with a lot is that HHVM is a big binary itself. Like, we're compiling a big program, but it's a big binary itself. And when you run a PHP program, we're going to access pieces of our code, like the internals for arrays or the internals for the compiler. And where those are laid out in memory and what order, it matters a lot for performance. And we've struggled, like, with the compilers being able to optimize that really well. And a lot of our lockdowns were basically just manually moving functions around and annotating them so that they came out fast in the compiler. And finally, Bert on our team came up with a great hack, and he used the Linux perf tool to figure out which functions are the hottest, write a script to list them in order of hotness, and then we linked the binary that way. And we call it Bert's heuristic, and that's what gave us this big step function right here. If you basically just take the functions in your C program and put them in the right order according to how often they run and how big they are. So these, never mind the math. It's basically hotness per byte is what we've come up with Bert's heuristic. And this gave us, like, in one change, there's a few lines of code to write this script, like a 3 or 4% win. I mean, that's unheard of. Like, that never happens. There was dancing in the streets. There was partying that night. It was great. This was a wonderful thing. If we ever see one of these, we're just, like, ecstatic. And then we did some more things. And later on, about a week later, we found some ways to use Bert's heuristic in addition to a call graph, which I won't go into. But we basically got even more out of the same idea. And this was, like, the biggest lockdown we've ever had. This was amazing. So that was last year. Now we're talking about this year. More memory optimization, more bytecode optimization. We can take the whole giant hundreds of megabytes, hundreds of lines, or excuse me, millions of lines of code, analyze it all at once. We have a new optimizer that does that, that's better than the old optimizer that does that. New is better, old is worse. We have a region compiler, which I described. And it's only the beginning of the year, it's April. So what are we looking after? Where are we looking ahead to? And this is, like, where I'm really optimistic about PHP performance. I talked about all these little things that we do. If you look at, like, the state of the art of virtual machines, like, we still have some work to do. And what I'm going to do is just describe, like what the work is ahead of us. But the thing is, like, these are meaty projects ahead of us, and this is why I'm optimistic that we can get, like, a lot faster from where we are, because we just haven't done these things yet. And so one is continuing to shrink the data structures. We have new tools that allow us to see new memory access patterns that's going to let us reorganize our data structures to have even better memory locality. Hack now gives us type annotations, which, using our new, better whole program analyzer, we can actually use those type annotations to remove some of those guards. So our region compiler will let us remove some guards, but with Hack, we hope to be able to remove guards in some cases where they're just never even there and you never have to check the types because we've proven statically that it's the type we expect. Cluster-wide profiling. We were talking about a CPU. Well, a CPU sits in a data center next to thousands of other CPUs doing the exact same thing. Well, could we take advantage of that somehow? This seems like a big advantage. Clang and LLVM are really robust compiler technology that we would have to replicate if we do the same things, and we're interested in evaluating them. And garbage collection. Our garbage collector is still reference counting, which is sort of the, table stakes for any kind of dynamic language, but it's really nowhere near as far as you can go. If you look to what's in a JVM, it's far more advanced than what we're doing, and so we think there's upside in true garbage collection. So, thanks for listening. I told you what we did. What do we do? How do we do it? What have we done? What are we planning on doing? By the way, let me back up. We doubled the performance. That's, if you think in terms of like being excruciatingly happy over a 1% win and ecstatic over a 4% win, we did a 50% win last year. We're going to go, which means doubling performance. We're going to try and do that again this year. And next year, we're going to try to do that again, and we're going to try to keep doubling the performance year over year. And so eventually you hit an asymptote. Like eventually you just can't go any faster. The laws of physics have to kick in at somewhere. But I feel fairly confident that we're at least 2 or 3 years of doubling before we hit that asymptote. And up there at the other side of the asymptote is where you see JVMs, where you see V8, the engine for JavaScript. I think we have a little bit of ways to go, and I'm really excited to do it. This is our team from the end of the lockdown. There's some familiar faces in there, I hope. Thanks. And did I go over? Do we have time for some Q&A?
Maybe one.
Yep. Anybody? Go ahead.
Anonymous person online. How does performance of Hack on HHVM compare with performance of regular PHP on HHVM?
Today, the performance of PHP on HHVM and Hack on HHVM are about the same. All those type annotations that you put into your code are basically just ignored by the VM. On the one hand, this allowed the Hack type checker and our runtime to evolve separately, and we could each pursue our own goals without coupling too tightly. But in the long run, we hope that Hack will be advantaged by those extra type annotations. I mentioned that briefly in the talk. But right now, they're the same speed. Any other questions?
Yeah, we'll get one more.
So as just a developer who works solely in higher level code than your presentation really hits on, what can I do to actually help my code perform better, to take advantage of keeping my application CPU bound as opposed to operating in RAM and that kind of thing?
I think there aren't, I don't have like a cookbook of things you can do, but I think the best thing you can do is try to keep your data in array, like vector in Hack, right? If you can keep your data stored in like linear organized data structures, that helps. And if you can keep your code small and not like code that sprawls and jumps all over the place is slow. Code that runs in a tight loop or uses built-in primitives in the runtime tends to be much faster.
Another way you could do it is just swap runtimes to HHVM. Things get faster for free.
I mean, I guess they should plug the tools as well. We're working on tools that allow you to actually measure your code and see if it's fast or slow, and where is it fast and slow, and work from there. So being data-driven is a lot better than just sort of working off of cookbooks. That's what we do. That's what I would recommend you do also. All right. Thanks, everybody.
Thanks, Ed.